Day 4, what we're looking for. Hi and welcome to another episode. And what we've got here is the PiHut Advent Calendar, the 12 projects of Codemas. Day 4. Let's open it up. What have we got? What have we got? I know what we've got. I can tell what it is. It is bits and pieces. There we go. We've got a jumper wires made to mail, and we have a variable resistor with a cap and a washer and a nut to lock it all into place. So we're just going to put it on there so we don't lose it. Obviously we're not plugging it into anything right now. I don't know how this is going to work because we have this and then we have jumper wires. So we're going to just jam that in. Who knows? Let's find out with the instructions. Day 4, Amazing Analog. Welcome to day 4 of your 12 projects of Codemas Advent Calendar. Today we're playing with the analog inputs using a potentiometer and combining this with some of the components we've already played with. Variable resistor, potentiometer, potato. Our code so far has been on-off or high-low using digital inputs and outputs. With today's component, we're going to explore analog inputs, which work in a different way. Let's get the mouse pointer over. Tip: you'll find that some people in the maker will use analog and others prefer analog with a UE. It's all the same thing. Basically, depends on which side of the pond you live on, pretty much. Anyway, we've got a 10K potentiometer, a potentiometer knob, a washer, maybe fitted to potentiometer already, a nut, maybe fitted to potentiometer already. Mine wasn't, but yours might be. Male-to-male jumper wires. Okay. Today's project. Today we're exploring the wonderful world of analog. Until now, we've been using digital signals for the buttons and LEDs in our calendar. Digital signals are strictly 1 or 0, high or low, or on and off. It's one or the other and nothing in between. Analog signals offer a wide range of numbers to represent values instead, which is much more suitable for sensors, dials, and similar components. Think of digital as a light switch, it's either on or off. Think of an analog as a volume dial on a stereo. You can twist the dial to gradually turn the volume up and down by small amounts. Or it could be a dimmer switch on your lights, if you can use one of them. Our potentiometer can pass these analog signals in the form of voltage to our Raspberry Pi Pico, giving us a gradual input with a wide range of values for us to play with in our code. What is a potentiometer? A potentiometer is a variable resistor. Dun 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 dun! Right. Our calendar already included the traditional resistors for the LED, but these were at a fixed value offering a specific amount of resistance. A potentiometer is a resistor that can have its value changed by turning the knob. Da, da, da. The potentiometer, I'm going to stuck that down there now, haven't I? Always difficult to get back off again. There we go. Right, I recommend you twist it all the way to the left and try to decide where your maximum and minimum are. That's that way, so I'll put it that way. And you can twist it all the way around. There we go. So we have it all the way to the max. And I'm personally going to have it. The max is all the way over there. Bit of a tangent, but that's what I'm doing with it. There we go. Ta-da. Right, where were we? The potentiometer is in the box a 10K potentiometer, meaning it's set to anywhere from 0 ohms to 10,000 ohms. Resistance is measured in ohms. The way we're going to wire our potentiometer allows us to send a varying voltage value to our Raspberry Pi Pico, which some special pins can read, convert, and provide a value we can use in our projects. We're going to explain those pins in a few moments, but for now, let's get the circuit built. Construct the circuit. Make sure your Pico USB cable is unplugged before changing the circuit. Let's make sure then. It is, it's already unplugged. Right. Grab your potentiometer, slide the flat washer over the dial and then screw on the included nut. These may already be fitted. Then with the potentiometer legs facing downwards, turn the dial all the way to the left and fit the knob with the coloured line pointing to the bottom left, which is what I've ended up doing anyway. So twist it all the way to the left, and then with the red mark, let's zoom in a little bit, or a lot even. I went off a bit of a tangent and told you how to do it, but they're telling you to. Basically, twist it all the way to the left, and then stick it on with that red bit pointing at the left circle, and then we can do that, and it will point into the right one when it's on full. That's what you're aiming for. Okay. Right. Let's zoom out again because I always forget to do that. Then with the potentiometer legs facing downwards, turn the dial all the way to the left, hit the knob, blah, 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 blah. Light the radio all the way down. Leave the LEDs and the ground wire in the blue lane. Leave the LEDs and the ground wire in the blue lane in place of yesterday's box, but remove the buttons and all the other parts. Okay. So that wire comes out. That wire, that wire, that wire, that wire, that wire, that wire. That's the buttons out of the way. And the LEDs are all nicely wired up still. Yep. Fine, we've got that far. Now grab the mini board. Oh, we've got to actually remove all the bits from the mini board as well. It'd say to do that, but I didn't know if it meant just to take all the things out of the way. Put them all there. Potentiometer. Now grab the mini breadboard and fit the potentiometer to the front edge facing you. Our diagram uses a generic potentiometer image. However, as you have a fancy panel mount version, your pins will have a whole space between them. Okay. So missing two holes to the side and then pushing it in. There we go. So it looks like that now. Next we need to connect the potentiometer to the circuit. Let's grab some wires. They happen to have a red one on the right hand side, so I'm grabbing that. If you look down the back here, you'll be able to see that you've definitely got the pins lined up. So top row, but underneath that bit there. So this row, we're going there, and then we're connecting that pin 36, which is actually J5 on our breadboard. I'll just use a yellow wire going 2 across to the left from that last one, so there's a gap in between, and that needs to go to pin number 27. So we've got 36, 35, 34, 33, 32, 31, 30, 29, 28. That can't be right. Ah, it's 32. It's GP of 27. See, double check what you're doing. So 26, sorry, 36, 35, 34, 33, 32. I definitely need to get more sleep. Sorry for my messing about. Right, another wire. They happen to be using black on the diagram. But then we need from the blue lane. So we have connected that to the LEDs. So the left pin to ground. So we're just going to use. We just need to use the blue line area, but we're just going to use the same area that they've used. So it's actually this one that I'm selecting. It's on the blue line area below pin 14, if that was a thing on the there. And then we're connecting that up without trying to knock other wires out of the way. Next two on the left of that last one on here. So you should have gaps like that, all matching up to the pins. So basically, yeah, it's the same as where this thing is. This is turned all the way down. Printing analog values. Let's move this down a bit so we can see what we've got as well. Let's start with a simple program that continually prints the analog reading from our potentiometer. We're specifically using a GPIO 27 as this is the one of the Pico's ADC pins. But what is an ADC? ADC pins, if you look at the Pico pin map, which I'll let you do, you'll see that there are 3 dark green ADC pins available on the right. GPIO 26, 27, 28, physical pins 31, 32 and 34. An ADC is an analog to digital converter. The ADC pins on our Pico have this special ability to being able to convert analog input into a digital form we can use. We have to import ADC in our code to use this feature. Note, you'll also spot that ADC_VRF and AGND pins, so that's A ground I suppose, but we're not going to be going to those pins in this calendar as we don't strictly need to use those pins for example. We'd rather not overcomplicate things whilst we're still learning. The code. The code below imports ADC and sets the GPIO 27 to ADC pin. Then we start a while loop which prints the potentiometer values every second. The read_U16 part does this, taking the varying voltage applied to the pin from the potentiometer for scaling this range of a usable output values from 0 to 65,535. There's a number when it comes to computing of 65,536 becomes a very common number to you. You'll understand if you want to get into programming more than what we're playing around with this. I'm not going to bore you with that for now, but it sort of comes up with the times that you'll come across. Well, it's binary basically, and you'll learn that 8, 16, 32, 64, 128, 256, so on and so on. It gets up to 65,536. For those that want to get technical, the Pico's ADC pins are 12-bit, however, 12-bit. However, MicroPython scales this to a 16-bit range, which is 0 to 65,535. Run the code below and try turning the dial. Watch the values go up and down as you turn the knob from right to left. The values don't always get down to 0. This is normal. This is where everything above should start to make sense. Okay, so we'll copy this code, slap that in. As I say every day, we need to get used to typing these things in instead of just cutting and pasting. But what do we need to do right now, which they always forget to tell us, and I always forget to do, is we need to plug it back in again, don't we? So I'm going to plug it back in, and I'm going to zoom out a little bit because we're a bit super close at the moment. Who knows, man, start playing around with the LEDs again at a later part of today's activities. So we've got a potentiometer, we've got a little board going, we've got that code, we've plugged it in, we need to press stop to make it find it, then we press run, and now it's got a value straight away which is bouncing around, even though I'm not touching it. Now we'll turn it up, so you can see the red line at the top there. Actually, I'll tilt it a little bit so you can see. And that's full blast now. If it was a volume control, and there you see 65,535. Turn it all the way back down again, and it sort of bounces around a fair bit actually. But that's the first activity done. We'll stop that for now. Activity number 2, controlling LED flashes with analog values. Must have read that without realizing I'd read it. So what can we do with the large range of input readings? One thing we can do is use in our code is to control the other components such as our LEDs. Whereas previously we have turned the LEDs on and off with buttons, the wide range of output readings always allows us to tell our code to do different things depending on whereabout in the range. The code below uses the readings to control how fast your LEDs flash. We do this by making a time delay variable. Variables for time delay. We use the variable to make the counter in day 2, which is constantly updated. This time we're using the variable to allow us to set a value in one place rather than having to search through our code for all the various time delays. For example, let's say that we had 5 LEDs in our code and we use a time delay of 1 second every flash. From what we've learnt so far, we would use time.sleep open bracket 1 close bracket after every flash. That works fine, but it's a bit of a pain to update all these lines every time you want to adjust the flash speed. Instead, we can create a variable and assign that name to such as myDelay and give it a value of, say, 1. We can then change the time delay lines to refer to the variable instead of entering the number directly. Using time.sleep myDelay instead, now the update is the speed of each flash across the entire program. We only have to update the myDelay variable. Whilst we only use the delay once in the example below, we thought it'd be still nice to opportunity to show you another way of using variables to save you time and improve your code. The code. The example code below takes a reading from the potentiometer, divides the reading to give us a number that's more usable as a time delay, assigns the divide reading to the variable myDelay, uses that delay variable to control how long the LEDs are left on and off to create a flashing sequence. Turn your knob halfway to start with, run the code below, then try adding in other LEDs and making them flash as well, or trying to add a print line at the end of the whole loop to see what variable myDelay is using. Okay, let's get rid of that code, copy it and stick it in. I did say to set the potentiometer to halfway, so that's roughly halfway. Stick the code in, run it. So red is flashing. Now it's doing a slow flash. I've turned the potentiometer up full whack. Turn it all the way down. And basically it's staying on now. So there's obviously some kind of misreading there, but or maybe it's just flashing so fast we can't see it. I think that's what's actually happening. Actually, I don't think it's on all the time. I think it's flashing. But there we go. We've got some flashing going on. Not particularly. Oh. Maybe they should have warned us about photo sensitivity epilepsy. Sensitivity epilepsy. That they haven't done, but it is only on a tiny small video. But yeah, you play around with the code and see if you want to add in other LEDs. I'm just going to try to get through this pretty quickly. If you get stuck, you can always come across to my Discord and have a chat there, or just leave comments in the description, not the description, leave comments in the comments part of the video so that other people can maybe help you as well. Let's go on to the next activity. Activity number 3, light LEDs depending on the potentiometer value. We can use the wide range of analog values to trigger an action depending on whereabouts in the overall range we are. We can do this by using if statements again, this time with conditions that look to see if the value is higher, lower, or in between the set range. In our example below, we use a few of the statements to check to see if the reading is less than 20,000, between 20,000 and 40,000, or greater than 40,000. To make our if statement look for less than and equal to, we use the less than sign and equal sign operator like this. If reading is less or equal to 20,000, and basically the same again with this combination but this is actually incorrect. Wait a minute, is it? No, it's correct, isn't it? It's if 20,000 is less than the reading, but is the reading less than 40,000, checks to see if it's between 20,000 and 40,000. To make our if statement look for a greater than equal to, we use the greater equal operator. This is if the reading is greater to 40,000, right? Give it a spin by copying the code below over to Thony, running it on your Pico and moving the dial left and right slowly. Remember, the code commentary is there to help you understand each line. And we shall copy that code, paste it. As it says, it's telling you how that works. Very short delay. Let's run it. So if we change it now, put it onto yellow or amber and then onto green. You can tell that that must be going in between, and of course the green again. Right, let's stop that code. Activity number 4, LED fader using PWM. Now for something a little more advanced but really cool, we're going to fade an LED in and out using our potentiometer. To do this, we need to use PWM. What is PWM? PWM stands for pulse width modulation. It's a type of digital signal where we over a period of time, decide how long the signal is on, high or 1, or how long it is off, low or 0. This very fast on-off signal can create a fading effect for LEDs and can also be used to control robotic components such as servos. Servos are basically little motors that you can control if they're turning clockwise or anti-clockwise. Anyway, our code needs some values from us to enable it to run PWM for us. Duty cycle and frequency. What is PWM duty cycle? We can decide how long we keep the LEDs on or off, on or high, by changing the duty cycle. The duty cycle is the percentage of time the LED will be on. The higher the duty cycle, the longer the LED will be on, and the brighter LED will appear. Duty cycle for the Pico in micropython can have a range from 0 to 65,535, which is handy as it matches the output of our potentiometer. So we can use these values directly without having to manipulate it. What is PWM frequency? PWM code also needs a frequency value, which is the number of times per second that we will repeat the on-off cycle. We use 1000 in the example below. The code. So now that we know what a PWM is and duty cycle and the PWM frequency is, let's try it out. The code example below introduces a few elements. First, we need to import PWM. We set our LED pin out to a little differently, set in the PWM output using LED equals PWM bracket pin bracket 18 bracket. We set the PWM frequency with PWM.freq 1000 in brackets. We create the variable to store the potentiometer reading and start it at 0 using reading equals 0. The while true loop then reads the potentiometer value to stores this in our reading variable and prints this for us to view within Thony. The LED is then given the reading as the duty cycle uses LED.duty_U16 reading. This is followed by the very short delay, then the loop continues. Copy the code below into Thony, run it, and turn the dial left and right. Okay. Copy, paste. Let's run it. Oh, it's very, very dim. Right, I'm going to try to turn the lights off so you can see what's happening in the camera. Just had the echo with no name. Turn off my room lights. So we can see it's glowing. It's very, very low. I can For me, the LED has got a little red dot in the middle of it. It's not as bright as what it looks like on the camera, to me. So let's move the potentiometer backwards and forwards so we can see the values increasing. And now it's bright. Quite frankly, it doesn't seem as bright as it could be, but it is brighter. Yep. Definitely an analog control. Let's stop that code again. There's a lot to be read in the commentary of what's happening, so have a read of that. That's day 4 complete. Well done, makers. We know today was a little heavier as we introduced slightly more advanced topics such as analog, PWM. So take the time to go back over today's examples and play with the code if you'd like more practice. Make it, break it, fix it, learn it. Today you have learnt about analog and differences between analog and digital signals, built a circuit with a potentiometer, learned how to use an ADC built into the Raspberry Pi Pico, controlled LEDs with an analog signal, learnt about PWM including duty cycle and frequency. Keep your circuit safe somewhere until tomorrow. Don't take anything apart just yet. See you then. Well, that's them signing off, and as for me, don't forget to have a look in the description for links towards my Patreon and Discord. Don't forget to hit the like button, the subscribe button, and the notification bell to find out what happens tomorrow. But as always, happy gaming.